Today I will talk about placenta vesicles, their vascular effects, and their potential role in cardiovascular risk after preeclampsia. And I will go through some new mechanisms that we have discussed. The project wouldn't have been possible without Chris. We worked with him for 10 years, and we got vesicles isolated from placentas from Oxford, and we worked with Chris, Dion Tanetta, and Ian Sargent in this project. So Chris been a real mentor and a good friend over many years, and he's greatly missed in many ways. I would like to disclose that I've been the co-founder of a drug company, Guard Therapeutics. We used alpha-1 microglobulin as a new potential drug to treat preeclampsia, but also treat situations where you have high amounts of free hemoglobin. So free hemoglobin has been a story in my lab since 2007. Magnus Entlund, then a PhD student, he did omics studies, and we could see that free hemoglobin was accumulated in the preeclamptic placenta. In the picture is an in situ hybridization showing that the white cells here in the lumen of a normal placenta, they express fetal hemoglobin. And the bottom panel shows a preeclamptic placenta, and you see cells in the lumen, but also in the interstitium. We did immunohistochemistry, and we could see that the preeclamptic vessels were clogged with free hemoglobin. So where it came from was yet another puzzle we wanted to solve. So we looked at cord blood from banked blood from 15,000 pregnancies, and those were normal pregnancies, and we had 444 preeclamptic pregnancies. And we could see that in the venous cord blood from preeclampsia, there was a higher level of hemoglobin, fetal hemoglobin. We looked at the hematopoietic stem cell progenitor cells from the cord blood, and we did transcriptomics, and we could see that the mTORCH APEC-UK signaling pathway was differentially expressed. That's a pathway that controls cell cycle, differentiation, and protein synthesis. And this was particularly pronounced in male pregnancies. So free fetal hemoglobin is also a toxic compound. As soon as you have a situation where you get hemolysis, the hemoglobin starts to be degraded by different enzymes. Hemoxygenase is a rate-limiting enzyme. But the degradation metabolites such as heme, methemoglobin, and iron, they all cause oxidative stress and creation of radicals. And that causes oxidation of tissue, cell and matrix damage, inflammation, and vasoconstriction. So we came up with a model where free hemoglobin is a placental toxin. We have hematopoietic stem cells circulating in the fetal blood, producing hemoglobin. When they come into the preeclamptic placenta, where we have reduced perfusion and a more hostile environment, we get oxidative stress, apoptosis, and leakage of free hemoglobin. So it becomes a vicious circle with more radicals, more inflammation, and endothelial damage. On the surface, the vesicles are released, and they end up in the maternal circulation, where they cause inflammation and endothelial damage. So let's focus on the syncytial trophoblast vesicles. they are released from the surface and they end up in the maternal sleeve. They were described by Redman and Sargent in 2008, and they have done a lot of work on them, and they have characterized them looking at their content. They contain different proteins, DNA, RNA, and microRNA. The beautiful thing with microRNA is that you actually have placenta-specific microRNA derived from the cluster 19. It's a specific chromosome that produces those microRNA. And altogether, the vesicles, they forms a signaling pathway between the placenta and fetus with the maternal different tissues, most of all the vascular bed. So they can be formed by microblebbing, so you form larger vesicles, or by exocytosis, there you form smaller vesicles. In Oxford, they also got vesicles from placentas by using the placenta perfusion model. This is a schematic drawing of the model by Adam Brook in Manchester, and the original model, the dual placental perfusion model by Henning Snyder. There you have oxygenated media that you circulate both on the maternal and fetal side, and you can keep the placenta alive for up to 6 hours. The Oxford, they used a different modified version of the perfusion. You can also isolate vesicles from plasma, and you can use ultracentrifugation. There are different protocols. Once isolated, you can show their size by using a nanoparticle tracking device. You get a size distribution pattern, as you can see. You can also use Western blot. There you identify the placenta-specific alkaline phosphatase that's on the surface of the vesicles. And we also use the electron microscopy to show flap on the surface, but also placenta-specific microRNA in their lumen. And we could also show that they do contain fetal hemoglobin. So our hypothesis was that the vesicles entering the maternal circulation could be taken up by endothelial cells. So we used human coronary artery endothelial cells in culture, and we incubated them with vesicles. And the vesicles were dyed with a fluorescent green, PKH67. And here, after a couple of hours of incubation, you can see that the endothelial cell, they take up the vesicles with small green dots. You can visualize the same thing with electron microscopy. Here is the plasma membrane of the endothelial cells. You can see how the vesicle is docking on to the surface. And since they contain microRNA, we did a screening of the different microRNA in the preeclamptic vesicles. And we could see that one of the differentially expressed microRNA was 517A here. So it's a lower expression in the preeclamptic vesicle compared to normal tensing vesicles. The other microRNA were constant and likely more of housekeeping version. What we could see as a target for the microRNA 5178 is FLT1. And interestingly, after taking up the vesicles, we saw a downregulation of FLT gene, both in normal, but a little bit more in the preeclamptic vesicles. So we see a reprogramming of the endothelial And in the literature, we read about chlorpromazine that has a specific latrine blocking effect. And by using that, we could show a dose-dependent blocking of the vesicle uptake. And the blocking was as pronounced in the normal vesicle as in the pre-eclamptic. But we concluded that the uptake was mediated by latrine, and chlorpromazine 1 drug blocked the uptake almost 100%. Aspirin did not have an effect on vesicle uptake. We then wanted to study more full-bodied vessels. So during C-section, I collected subcutaneous tissue, and from the subcutaneous tissue, we then dissect smaller vessels, and we cut small segments and we put them in a wire membrane. And it's a system that allows you to measure the contraction of the vessels. We incubated the vessels for up to 24 hours with vesicles from either normal pregnancies or pre-eclamptic pregnancies. And then we looked at the contractility. And what we could see was that the pre-eclamptic vesicles, they induce a significant contraction in the vessels, here shown in red. And the most interesting was that the normal vesicles, they actually had the opposite effect. So we induced vasodilatation. The effect on both normal and pre-eclamptic could again be blocked by chlorpromazine, and even more so in the pre-eclamptic ones. And up to the left, you see the area under the curve for the different experimental setups. Another striking difference was that the normal vesicle, they did not cause any damage to the endothelium. So they were maintained intact with nice structure and intact collagen. But the pre-eclamptic vesicle, they induce damage to the endothelial cells. As you can see here, the collagen is completely degraded in certain areas. So in conclusion, we have seen that the vesicle from placenta contains specific microRNA and free fetal hemoglobin. They are taken up by endothelial cells via clathrin-mediated uptake. And the clathrin-mediated uptake can be blocked pharmacologically, and in this case, used chlorpromazine. The STBV microRNA content has the ability to reprogram the endothelial cells, at least in vitro. The vesicle-induced vasoconstriction that's mediated by angiotensin II receptors. And normal vesicle, they actually induce vasodilatation. The pre-eclamptic vesicle, they disrupt the structure by inducing oxidative stress, and that we don't see in the normal vesicle. So we propose that this might be a future prophylactic treatment to reduce future cardiovascular risk by one, reducing contractility of the vessel, but also to prevent the reprogramming that might be the underlying mechanism for the vascular stiffness that you see on the eclampsia. So I would like to acknowledge particularly Chris Group and Dion Tanetta that we work with. And I would also like to thank my PhD students and my collaborators